Hi everyone, welcome back. Now today we're going to be talking about Taylor and Maclaurin series. Now this section is actually going to wrap up the chapter for us on sequences and series. And so what I want you to do to start off this section, I want you to recall what we were doing with power series in the previous sections. We were able to say that we were able to grab a power series notation for a function that had a radius of convergence r greater than 0 and an interval of convergence of a minus r all the way to a plus r. So in other words, we were looking at this interval of convergence with this radius just being the absolute value of x minus a being less than r. Alright. Now, what I want to do then is I want to build upon this a little bit more. I want to extract a function here, a function that's going to be represented by this power series. Now, when we have this, I just want to expand this power series to look like this. Perfect. So once I have this, in the previous sections we learned that once we have a power series representation with the interval or the radius of convergence, then what we can do is we can start applying calculus to it. We can start taking derivatives, or we can start taking integrals, so on and so forth. And that's exactly what I want to do at this point in time. I want to start by looking at a derivative. So I want to start by looking at f prime of x. Oops, let's make this a little bit nicer. Here we go. So I want to start looking at f prime of x in this particular case. Now I did this term by term so that we can start seeing what's happening to each individual term. As I take the derivative of the constant term, that's going to go to 0. As I take this derivative here with respect to x, remember x is the variable, so as I take this derivative with respect to x, we just get c1 plus taking this derivative now for this third term, it's going to get us, drop that exponent forward, 2 times c2, here we are, times x minus a, plus taking this derivative will leave us with 3 times c3 multiplied by x minus a to the power of 2, plus taking this derivative here, 4 c sub 4 times x minus a to the power of 3. And again, we keep on doing this as long as we want, or towards infinity. And again, this is all still for the same radius of convergence. Now, analyzing this, I then want to start taking a second derivative and see what's happening there. Alright, so let's go ahead and let's take that second derivative then. So f double prime. Once again, this first term on the first derivative goes away because that's a constant term. And then here, for the second term, taking the derivative with respect to x will just leave me with 2 c2. The next term will leave me with 3 times 2 times c sub 3 times x minus a, plus the next derivative will leave me with 4 times 3 times c sub 4 times x minus a to the power of 2. And again, we can just keep doing this as we tend to infinity. Now, this looks pretty cool so far. Now, I'm going to go through and I'm going to do one more derivative. Alright, so we took a first derivative, we took a second derivative, let's take a third derivative just for fun. I know I might have a different definition than fun, but than everybody else, but it's okay. Alright, so again, looking at the second derivative, my first term here is going to go away because it's going to be a constant. So the derivative then starts here, which is just 3 times 2, looking good, times c sub 3. Alright, looking pretty good. Plus the next one here, which is going to be 4 times 3 times 2 times c sub 4 times x minus a to the power of 1, because we subtracted 1, and then we can just keep on doing this forever. Nice. Now, why am I doing this, right? Why am I looking at this? Well, the reason I'm looking at this is because I want to then start extracting a very important observation that we can see from here. So what I'm going to do right now is I'm going to use excuse me, I'm going to use x is equal to a, and I'm going to use x is equal to a for f of x, f prime of x, f double prime of x, and f triple prime at x. Alright, so now that we have all of those derivatives expanded, we can then again start looking at this. So if I look at f of a, and that's going to be the first one here, substituting the value for f of a here, what's going to happen is the second term, the third term, fourth term, fifth term, so on and so forth, they're all going to cancel, which means my original function evaluated at a just gives me my constant term. Okay, that's pretty cool. Well, what about f prime at a? Alright, so f prime at a here, that means the second term is going to cancel, the third term is going to cancel, the fourth term is going to cancel, so on and so forth, because they all have x minus a. Again, substituting in here, it's just a minus a, which is 0. So naturally, I only get my constant term, which is just c sub 1. Let's look at my next one. F double prime at a. So f double prime at a now, again, substituting in a values, well, the second term cancels, the third term cancels, so on and so forth, which means we only get the constant term of 2 times c sub 2. Alright, looking pretty good. Let's look at one more. And this is the last one that we got to look at. Third derivative at a. Third derivative at a, well, yeah, you all guessed it. Every single term is going to cancel except for the constant term. And the constant term has us as 3 times 2 times c sub 3. Now notice here, I didn't actually go ahead, I didn't actually multiply 3 times 2. Instead, what I have it done here as is I just have it in explicit multiplication form. So, what does this look like now? Or what does it look like it might be happening? Well, what we want to do then is we want to analyze this pattern. Alright, so let's analyze the pattern then. So what I see here is I have f of a is equal to c sub naught. Alright, so then the first derivative then is going to be this second coefficient. Then the second derivative is going to be this third coefficient multiplied by 2, so on and so forth. So there does appear to be some sort of pattern, and I want to establish that pattern. So the observable pattern then that we then start looking at is that we're going to be taking some function with some derivative, or for some derivative, I'm going to say the function with the derivative of n, alright, to the nth derivative, evaluated at a, is going to give me, now watch this, n factorial multiplied by c sub n. Now, does this hold? Let's double check. Alright, let's verify. So let's verify the assumption, or the observation. Alright, so let's verify the observation. First derivative, if n is equal to 1, or sorry, let's say n is equal to, excuse me, in this case, if n is equal to 0, that means we're not taking any derivative. That means we're just going to be looking at f of a. Then that means in this particular case, this is going to be 0 factorial multiplied by c sub 1, or sorry, c sub 0. Remember what 0 factorial is. 0 factorial is just 1, which means this is just c sub naught. Oops. Let's look at the next one. N is equal to 1. So that's the first derivative. So n is equal to 1, that's the first derivative, then that means 1 factorial. So 1 factorial multiplied by c sub 1, then this is just c sub 1. Looks like what we got here. Alright, let's look at the next one. N is equal to 2. Second derivative. Alright, that means n is equal to 2, so second derivative here, f of a, That's 2 factorial multiplied by c sub 2. 2 factorial is just 2, so that's just 2 times c sub 2. That's exactly what we got. What about n is equal to 3? Well, that's a third derivative. That means that I'm going to have 3 factorial multiplied by c sub 3, which in this case, 3 factorial is 3 times 2 times 1 times c sub 3. And is that what we have here? Yeah, that sure is. The only thing is that we didn't denote the multiplication by 1, but that's okay. We've kind of learned to observe that it's always there. So our observation that there is a pattern existing here actually suffices to show that, hey, this is a pattern that we're initially looking for. So why am I looking for this pattern, right? What was the whole process for this, or why do I care? Well, the process of why I care is actually right up here. Look at the original formula. The original formula for the power series. The original formula for the power series has a c sub n. So what is that c sub n? And could we then find a formula for c sub n? Well, the answer, ladies and gentlemen, is right in here. Now that we have that observation, or better yet, now that we have this at our disposal, we can solve for c sub n. Solve for c sub n. That means c sub n, in this particular case, is the nth derivative evaluated at a divided by n factorial. Wow. Isn't that just mind-blowing? That is amazing. I don't know about you guys, but that is amazing to me. So what we have here now is we have a formula to actually express all of the constants on this initial power series. That's pretty cool. So let's go back and let's write it out in form of a theorem now. All right, so I'm going to write the theorem out, and then we're going to go ahead and discuss that theorem. So here's your theorem. The theorem basically summarizes what our discovery was right up here. The theorem says that if f, meaning the function, has a power series representation, and that power series representation is given by what we started with here, for that interval of radius and interval of convergence being absolute value x minus a is less than r, then its coefficients are given by this formula here. And that formula is the one that we were just discussing. Awesome. So, using this now, we can now start reinterpreting. We can now start reinterpreting that power series in terms of these given coefficients. And that interpretation is known as your Taylor series. So, let's go ahead and let's start writing what a Taylor series is. Because all it is at the end of the day, it's just a power series with the coefficients more explicitly represented. So let's go ahead and let's write that out. Alright, so here's the formula for Taylor series. Now, Taylor series, again, it looks very, very similar to power series, but again, we're making that interpretation that every single constant now has this specific form, which is the form of the theorem that we have up above. Awesome. Now, what we're also going to do is we're also going to talk about a special case of Taylor's theorem. So a special case for Taylor's theorem is going to be when we start analyzing and we start looking at x is equal to 0 and seeing what that gives us for this specific value, or for these specific values of Taylor series. Alright, so the Taylor series again is when we're looking at the power series being expanded at x is equal to a. Now, if we start looking at when a is equal to 0 or when x is equal to 0, then we get a special case. So we actually get a special case of the Taylor series And that special case of the Taylor series is when we're looking at the Maclaurin series. So here we get a special case when A is going to be equal to 0. Now, when A is equal to 0, then we're naturally going to get the power series here. So when we get that power series, what we're also going to do is we're also going to start analyzing what is taking then place. So special case when A is equal to 0, here we actually get the Maclaurin series. So let's go ahead and let's start writing what the Maclaurin series is then. Alright, so here's your Maclaurin series. Again, the Maclaurin series is going to be the exact same version of Taylor series, but with the only small added version that your A value is going to be centered at 0. Now, we would then want to start analyzing this Taylor series and this Maclaurin series. So remember what the radius of convergence means, or the interval of convergence means, when we're talking about a power series. The interval or the radius of convergence just basically means that we're going to have a certain radius or a certain interval in which this power series will converge onto a function, we call this f of x, such that it's going to model that function given that radius or in that given interval. So what I want to do is I want to show you a quick example of this on GeoGebra. That way we can go through and we can start extracting or visualizing this a little bit more. So please follow me along to GeoGebra. Alright, so here on GeoGebra I have the function for sine of x. And I've scaled everything appropriately here. I made the scale for the x-axis pi halves, and then the scale for the y-axis is just a scale of 1. And so what I'm going to do really quickly is I'm going to start modeling this function, this sine of x, using Taylor series. Taylor or Maclaurin. We'll see which one is which. So here's the first derivative, alright, or the first term. Notice that as x is equal to 0, when we're looking at our center point for x is equal to 0, this line, y is equal to x, kind of seems to be modeling this line, or this sine curve at this specific point. But as we move away further from that point, it's a less accurate model because we're creating a big error between those values. So let's use Taylor now, Taylor Polynomials, to start extracting. Look at this now. This is now degree 7. This degree 7, and again I went a really big degree really fast. This is a degree 3. Degree 3, notice how this polynomial, this G polynomial, this is my Taylor polynomial, how it's kind of modeling this sine curve. It's almost a really good depiction. Look at that, 12th degree polynomial. This is a 12th degree Taylor polynomial. Look at that 12th degree Taylor polynomial. Not only is it modeling it so perfectly here at x is equal to 0, look at pi halves, look at pi. The error really starts occurring on this interval here between pi and 3 pi halves and negative pi and negative 3 pi halves. That's where we start seeing this error that is occurring, or that these two functions are now detaching. But what if we keep on increasing that Taylor polynomial? Look at that, now it's a degree 23 polynomial. Degree 23 polynomial, wow, look at that. What happens then if we just keep going? Can you see what's actually happening here, guys? Look at that. This is my degree 87 Taylor polynomial. And look at that, just right over here on the interval from 19 pi halves to 10 pi, this interval, now we start seeing the error being created. So up until degree 87, wow, we were getting very accurate results. That is the power behind Taylor polynomials, or in this case, Maclaurin polynomial, because we're using our center as x is equal to 0, which means, hey, it's going to be the version where a is equal to 0. Now, what if we use Taylor a little bit more, let's say, not accurately, but let's say we use it a little bit more better? What if we're not going to center the polynomial at x is equal to 0? What if we center it at x is equal to a? That's where your Taylor polynomial comes into play. What we were looking at right now was your Maclaurin polynomials, or your Maclaurin series. The Maclaurin series is always centered at 0, which means it just expands from there. Taylor polynomials can be put or can be centered anywhere that we'd like it to be. So look at this case here. What I'm doing is I'm centering at 2 pi. Now in this case, I'm moving over to, let's say, at this point in time, pi halves. Let's look at it here. Go lower, there we go. So at pi halves here, notice a parabola models at pi halves really, really well. And this is, again, using the Taylor polynomial. Now, if I just keep on adding more and more terms to that polynomial, look at what keeps happening. I still keep modeling that polynomial or that sine of x. This means that Taylor or Maclaurin doesn't matter where Taylor polynomial is centered at. Look at that. I can move the center and it still models it really well for that given interval. But Maclaurin polynomial for that series, or Maclaurin series, is always centered at 0. Again, this brings up interesting results. So now that we are able to see a more realistic version of this, or we can actually envision this a little bit more, let's go through now and let's start analyzing some of these problems where we are going to be using Taylor or Maclaurin series. So let's go back to the whiteboard. Alright, so before we go on to an example, I want to start by saying that using calculus to model these curves or these functions that we're looking at kind of makes sense that we want to use Taylor series to elaborate on that, simply because if we're looking at the function and then the first and second derivative, then the first function is going to give us an ordered pair to lock in on, quote unquote lock in on. Second term is going to be the first derivative, where if you remember back from Calc 1, the first derivative actually allows you to observe what is the slope of the function at any given point in time. Looking at the second derivative, which is the third coefficient here, that second derivative allows us to then analyze the concavity that we then initially started looking at when we're talking about this first initial point. So naturally we have a point, then we have the slope, then we have the concavity that is being matched. And if we just keep on extending the derivatives or the coefficients, then we again naturally then start identifying these values or these terms that will be matching up with these coefficients or these specific polynomials. That's why we like to use Taylor polynomials to work with that. All right, because they incorporate those derivatives as we saw from the very beginning. Now, what we want to do at this point in time is we now want to start working with an example. So in here, I want to use or find the Taylor series for f of x, which is equal to e to the power of x, and this is going to be about x is equal to 0. Now, what's really nice about this is that because this is a Taylor series, well, Taylor series about x is equal to 0, in reality, or let's say in other terms, what I'm really asking you to find here when I'm saying Taylor series centered about x is equal to 0, this actually means that I'm going to be using Maclaurin series. That's what this tells me. And again, Taylor series, taking the special case when x and a are both equal to 0, then that's just going to mean, hey, we're going to be identifying the Maclaurin series. So let's now start interpreting this. Well, in order to proceed, I'm going to need a few derivatives to start analyzing what is this function that I'm looking at. All right, so that's what we need to start looking at. So I'm going to start identifying my function. Function here is e to the power of x. So my derivative, f prime, is itself. F double prime is itself once again. F triple prime, yeah, you guessed it, is itself again. That's the nice thing about e to the power of x. Now let's start looking at evaluating this for x is equal to 0. So x is equal to 0, this is going to tell me that my function here evaluated at 0 is just e to the power of 0, which is 1. My first derivative evaluated at 0 is just 1. Second derivative evaluated at 0, it's just 1. And finally the third derivative evaluated at 0, it's just 1 again. Which means that when we're using the Taylor series here, and I'm just going to really quickly write down the Taylor series, is equal to n, there we go, to the power of n. There we are. So what's happening here, as I start then observing this, well, my Taylor series, for my coefficients, my nth derivative evaluated at this a value, well, that derivative here is always going to be 1, which means this initial piece here, this is always, or at least my numerator, is always going to be 1. So I can generalize this a little bit more to say f prime of n at 0 is always going to be 1. So naturally, what we would then start looking to occur is that this numerator is always going to be 1, denominator is still going to be that n factorial, and then we have x minus a. Well, what's x minus a? A in this particular case is 0. So we naturally get this. Which means my Taylor series in this particular case is just going to be x to the power of n divided by n factorial. Expanding this, what does this now look like? Well, let's go ahead and let's expand this. Alright, n is equal to 1. That means if n is equal to 1, n is equal to 0. If n is equal to 0, then we naturally just get 1. Plus, n is equal to 1, then we naturally just get x. N is equal to 2, we naturally get x squared over 2. N is equal to 3, we get x cubed divided by 3 factorial. N is equal to 4, we get x to the 4th over 4 factorial. And we keep on doing this over and over and over again. This is the answer that we need. In other words, when we're looking at e to the power of x, e to the power of x, this function has this representation that we're looking at as its Taylor series expansion. Wow, that is awesome right here. Again, really, really cool and neat thing to see here, because again, now we're taking this function and we're expressing this function as a power series, or in this case as a Taylor series, which is really, really cool for us. Alright, not too bad. Alright, again, this can be thought of as a Maclaurin series because we're thinking of x is equal to 0. Now, let's see if we can do something a little bit slightly different. Find the Taylor series for f of x is equal to e to the power of negative x. And again, we're going to want to do this about x is equal to 0. Now, I want you to specifically do this for one reason. And that one reason we're going to discover after we do it, right? Along with a lot of things that we do. Well, why do we do them? Well, we're going to see why we do them after we do them. This is f of x. It's e to the power of negative x. Take the derivative. F prime of x now gets us negative e to the power of negative x. Take the derivative again. So second derivative, e to the power of negative x. Third derivative gets us negative e to the power of negative x. Awesome. I think this is enough to start seeing a pattern then. Let's insert the x value that we're given at x is equal to 0. So this is going to be e to the power of negative 0, which is just going to be 1. Next one is going to be negative e to the power of negative 0, which in this case is just negative 1. F double prime at 0, e to the negative 0, it's just 1. And then finally, third derivative, negative e to the power of negative 0, which is negative 1. So what can you see these constants doing now? Well, these constants are now alternating, which means, can we generalize this feature? Can we generalize those constants? Sure. Let's see. These constants are just alternating between 1, negative 1, 1, negative 1. So naturally, I'm going to start alternating these to some power, let's say n. Let's see if our n values now coincide with the terms that we're looking at. So at my original function, this is n is equal to 0. Negative 1 to the power of 0, it's just 1. Let's see the next one. N is equal to 1. If n is equal to 1, then negative 1 to the power of 1 is just negative 1. So this here looks like it's modeling these alternating coefficients, which is again really nice because now we can start analyzing my Taylor series. My coefficients are these pieces here, which is negative 1 to the power of n, divided by n factorial, multiplied by x to the power of n, or in this case x minus 0 to the power of n. Now, what does this mean then? Well, this means that we are looking at this polynomial. Alright, pretty cool. Pretty cool. This means, again, ultimately, that e to the power of negative x is equal to this Taylor series, as long as we're centering at x is equal to 0 for n factorial x to the power of n. Now, I want to expand this just so that we can start looking at it. First coefficient is just going to be 1. Alright, next coefficient, that's when n is equal to 1. So n is equal to 1, then we're naturally going to get negative. We get negative x to the power of n. We're going to keep going. N is equal to 2. If n is equal to 2, then we're going to get x to the power of 2 divided by 2 factorial, which is just 2. Oops, I wrote x to the power of n. Cheese and crackers. There we go. N is equal to 3 now. So if n is equal to 3, this is odd, so that means it's going to be negative. So it's going to be negative x to the power of 3 divided by 3 factorial. And we keep doing this on forever. So this is what e to the power of negative x looks like as a Taylor expansion about x is equal to 0. That's kind of awesome. Alright, so if we were to try to look at this algebraically, we can actually look at this algebraically as a polynomial expansion, and here's that polynomial expansion. Again, it's looking really neat. So, what we then want to analyze. Again, I said I wanted you to do this for one specific example or for one specific reason, and that reason wasn't going to be discovered until after we were done with the problem. Well, we're now done with the problem, so hey, Mr. Castro, why is it that we're looking at this now? Well, if you start looking at that expansion here, this e to the power of x, what we came up with was that we were going to be looking at x to the power of n divided by n factorial. Well, what happens then if we start looking at e to the negative x? Right? Now, you can think about this, let's say, in this particular way. What if we make this a t? There we go. And what if we now say let t equal to negative x? Well, what happens here then? E to the power of negative x, which is what we're inserting here, now becomes negative x to the power of n divided by n factorial. And what does this now become? Well, we can actually separate that numerator into negative 1 to the power of n times x to the power of n. Notice they both have the exact same exponent, therefore the bases are being multiplied. Negative 1 times x is just negative x divided by n factorial. So is this result the exact same as this result? Yes. And that result, we didn't actually need to go through this whole process. We actually just needed to make our insertion or our algebraic manipulation of the original Taylor series that we found for e to the power of x. So again, there are some easier ways around these Taylor and Maclaurin series. And again, all you have to do is then just try to interpret what is it, or what is the overall main function that we're trying to observe. Is it e to the x? Is it natural log of x? Is it 1 divided by 1 minus x? What type of function is it? As soon as we can find that out, then we can start making these assumptions, or we can start working with these more complicated functions. So let's work on a different example then. So let's now work on finding the Taylor series for this function f of x, which is e to the negative x, about x is equal to negative 4. So now this is no longer Maclaurin, because we're moving away from that x is equal to 0. Now we're looking at the Taylor series as it is. Okay, not too bad. So let's go through now and let's start extracting. See if we could find the derivatives for this function. That way we can make that conclusion of these are the coefficients that we're looking for. Not like the droids that we're not looking for, but the coefficients. I know that was a very bad joke. My apologies. I'm very bored here. Alright, so staying at the house is excuse me, very boring for the past few months. So now once again, looking at these derivatives, negative e to the negative x, there we are. F double prime at x is just e to negative x, and then f triple prime of x is negative e to the power of negative x. And we want x is equal to negative 4, so naturally we start making our insertions. That's the derivative. So this is going to be negative e to the negative 4, which means this is going to be negative e to the power of 4. And we can just keep doing this throughout the whole process. There we are. Which means, look at our coefficients. they're always going to be e to the fourth, but now they're alternating, positive, negative, positive, negative. So naturally, if I take the nth derivative evaluated at -4, then what I'm going to have here is I'm going to get -1 to the power of n multiplied by e to the power of 4. All right, that's my coefficient. So again, I want you to recall that Taylor function, Taylor series that we're initially working with. Let's copy that. All right, looking good. There we go. So I just want you to recall that. So now when I'm looking at my function f of x, which is e to the negative x, that has this representation for its power series, or sorry, its Taylor series. The coefficients in the numerator are these guys. That's -1 to the power of n, e to the power of 4, divided by n factorial multiplied by x minus a. But what's the a value? That's just -4. So this is x minus -4, which just becomes x plus 4 to the power of n. And there it is. This is your Taylor expansion for that polynomial e to the power of -x. Awesome. All right, guys, it's everything's looking pretty good so far. All right, looking pretty good. Now, let's try something a little bit more, let's say, kind of a complex. All right, a little bit more out there. All right, so here goes your example then. Find the Taylor series for f of x is equal to sine of x about x is equal to 0. Now, yes, granted, whenever I say about x is equal to 0, this really just means Maclaurin. Alright, so we again need to start looking at derivatives for the function, and that's where we start. Alright, anytime we're looking at Maclaurin or Taylor polynomials, we want to start looking at these derivatives. So let's look at this derivative really quickly here. So the first derivative, or sorry, the initial function is sine of x. Now I want my first derivative. This is going to be cosine of x. Next derivative is negative sine of x. Next derivative is negative cosine of x, and I'm going to keep going to the fourth derivative. So fourth derivative is just going to be sine of x. We wind up right where we started. Now I want to evaluate all of these derivatives at x is equal to 0, which means sine of 0 is going to be 0. F prime at 0 is going to be 1. F double prime at 0 is 0. F triple prime at 0 is -1. And then we get fourth derivative at 0 is going to be 0 once again. So do we get to see a pattern? Yeah, we actually do get to see a pattern, and that's actually going to be a really nice pattern that we're going to get to see. Now, oftentimes when you start looking at this pattern, you're going to see, wow, that's going to be kind of weird, because look at these coefficients. At the initial coefficient for the function evaluated at 0, we get 0. the next one is 1, then the next coefficient should be 0. So it looks like at these even, so beginning at 0, then 2, then 4, at these even coefficients, it kind of looks like it's zeroing out. So let's start looking at this in expansion form first. So let's look at the expanded version first. All right, so I want to look at the Taylor series expanded, that way we can see it. So the Taylor series expansion, if you notice when we come up here, this is the part of the expansion that I'm talking about here when I'm looking at Taylor series. This is the piece that I'm looking for. So I'm just going to copy this down below. All right, let's come back down here. There we are. So let's start looking at this. All right, let's move it upward just a little bit. There we are. All right, and I'm going to change the color here. Let's make it red. There we go. Perfect. So I want to start by looking at that Taylor expansion first and see if we can identify what the pattern is. So f of a, in other words f of 0, that's going to get me 0. So this first one here is 0 plus the coefficient for the numerator here is 1 divided by 1 factorial multiplied by x minus a. So this is going to be x minus 0 plus second derivative. All right, second derivative evaluated, that's going to get me 0. So 0 over 2 factorial multiplied by x minus 0 squared plus the next one. So the next coefficient in the numerator here, that's going to be a third derivative, so it's going to be negative 1 divided by 3 factorial multiplied by x minus 0 cubed. And then we keep on going. Or we could actually do the fourth term. Let's do the fourth term. Fourth term is 0 over 4 factorial multiplied by x minus 0 to the power of 4. There we go. All right, so what does this then tell us? Well, this now tells us that this term cancels because it's being multiplied by a numerator of 0, and this term cancels. So what do we really have left? Well, what we really have left is just this second term, which is just x, then this fourth term here, which is going to be negative x cubed over 3 factorial. Fourth term cancels. If we had a fifth term, what can you anticipate the fifth term to be? Well, the fifth term, they're alternating, positive, negative, positive, should be x to the fifth divided by 5 factorial. If we anticipated the next term, negative x to the 7th divided by 7 factorial. Again, these coefficients are alternating in sign. Next one would be x to the 9th divided by 9 factorial. And we just keep on repeating this over and over and over again. All right, I'll actually stop right here and say dot, dot, dot. Now, can we try to then find an expansion for this? All right, so let's try to find a formula for this. So the formula that we have that we're going to try to extract. So again, the x values are only odd and the coefficients are alternating. So let me tackle that alternating first. Let's do negative 1 to the power of n. Let's double check. Negative 1, n to the power of 0. So sorry, negative 1 to the power of 0, that's 1, so that's perfect. N is equal to 1, n is equal to 1. Negative 1 to the power of 1 is negative. All right, next one's positive, negative. Okay, so this captures the alternation. Good. Now I need x. X to the power of 1, x to the power of 3, to the power of 5, to the power of 7. I need to represent these odd numbers in terms of n. So I'm going to represent it as 2n plus 1. You can double check. If n is equal to 0, we get x is equal to 1. Sorry, x to the power of 1. If n is equal to 1, we get x to the power of 3. If n is equal to 2, then we get x to the power of 5. It's looking good. divided by the exponents meet the factorial. So that means my exponent was 2n plus 1, so this is 2n plus 1 factorial. There we are. This is your Taylor expansion for sine of x. Look at that. Isn't that now amazing? So when I showed you this on GeoGebra, I showed you this on GeoGebra and these polynomials. If I were to expand the actual expression for that Taylor polynomial that I was graphing, this is the expansion that you would see, or more general, this expansion is what you would see. Awesome. Very, very awesome. Now, what you can all do, see if you can try to come up with a Taylor series for cosine of x. So see if you can do that for cosine of x and see what you get, because it's actually going to be quite nice and quite interesting to see that. Alright, so I'm going to put a pin in that and I'm going to say you try to find a Taylor series for f of x is equal to cosine of x about x is equal to 0. Give that a shot. Put pause on the video, give it a shot, because I'm going to carry on with the video in just a little bit. So put pause on it and see if you can try to extract very similar process with what we did here. Very, very similar. If you follow this along, I guarantee you'll get the same answer. I'm going to do it a slightly different way so I can show you all. Alright, so again, put pause on the video, take your time, get this done, and when you're done, come back to it and see and cross-check, see if you got the right answer. Alright, so let's cross-check this. Now, what I'm going to be using is I'm going to be using the previous sections that we learned about power series. You know that, or we know that we can apply power series notation to different functions that we've come across, and once we apply that power series notation, we can actually apply calculus to it. So we can take derivatives or we can take integrals. So naturally, if I'm looking at sine of x, well, let's look at sine of x and let's see if we can take a derivative to get to cosine of x. So I'm going to say here, recall that the derivative of sine of x is cosine of x. Which means in order to get this cosine of x representation for Taylor series, all I need to do is take a derivative here for this Taylor series. Okay, not too bad. So let's see. So I know that cosine of x is the derivative for sine of x. Alright, that's what we know. Now the derivative for sine of x has this Taylor series representation. X to the power of 2n plus 1 divided by 2n plus 1 factorial. So when we take this derivative, again, we're going to take the derivative with respect to x, therefore the derivative can move through the summation. When it does so, we can now have the exponent move forward, so drop the exponent forward. So that's going to be 2n plus 1 multiplied by negative 1 to the power of n, x to the power of, and remember we subtract 1 from the exponent, which means subtracting 1 from the exponent just gets us 2n. Denominator stays the same, 2n plus 1 factorial. So now all we need to do then is observe 2n plus 1 divided by 2n plus 1 factorial. Well, this is kind of nice because 2n plus 1 for that numerator, denominator gets us 2n plus 1 times, subtract 1, we get 2n, then 2n minus 1. And we keep on repeating this till we get to 2 and then 1. What happens to the first term? Cancels. And all we're left with in the denominator then is just 2n factorial. And that's all we're left with. Which means this power series representation here for my Taylor polynomial, or my Taylor expansion here, is n is equal to 0, negative 1 to the power of n, x to the power of 2n divided by 2n factorial. There's your Taylor expansion for cosine. That's pretty cool. So again, we're using all of these tools at our disposal to say that we know how to do calculus with these series. Let's use it. Divided by 2n factorial. There we are. So if we can do this using, again, Taylor polynomials, and that is awesome. And that's what we want to, again, do. We want to go through and we want to expand this using those power series expansions. Awesome. So before we move on, we're going to start talking about some other examples that we can see when we're doing these Taylor expansions and see where they take us or where they lead us into. All right, so let's look at the next example. We're going to find the Taylor series for f of x being equal to the natural log of x about x is equal to 2. Alright, so we're going to go through and we're going to start, again, taking some derivatives here and start analyzing what it is that we're looking at. So again, f of x is my natural log of x. Derivative is 1 over x. Second derivative is negative 1 over x squared. Third derivative is 2 over x cubed. There we go. So 2 over x cubed. Alright, let's go to the fourth derivative. Fourth derivative, that's going to be negative 2 times 3. Alright, you can say 6, that's fine. X to the power of 4. Alright, looking good. Alright, now let's start evaluating at x is equal to 2. So x is equal to 2, so this is going to be f of 2. This is natural log of 2. Nice. F prime at 2 is 1/2. F double prime at 2 is negative 1/4. F triple prime at 2 is 2 over 2 cubed. Alright, we can say 2 over 2 cubed, so that's just going to be 2 over 8. Alright, we'll simplify in just a bit. The next one's going to be fourth derivative at 2 is that 2 times 3 negative divided by 2 to the power of 4, which should be just 16. Alright, so it's looking pretty good so far as to what we have here. So let's try to extract what's happening. Alright, so let's extract what's happening here, derivative-wise. Alright, derivative-wise, I see that we have an alternating sequence going on, so that's exactly what I'm going to account for, that alternating sequence. So let's go through and, whoa, hey there, hold your horses, look at this. First one, First function, positive. Second function, positive. Evaluation. Third evaluation, negative. Fourth one, positive. Next one, negative. So the alternating doesn't really begin until we consider the first, then second, then third, then fourth derivative. All right. So again, this particular case here was when n was equal to 0. These other ones was when n is equal to 1, then n is equal to 2, then n is equal to 3, then n is equal to 4. So it looks like n beginning at 1 all the way to 4 and keeps going. It looks like it's alternating at that point in time. So the alternating doesn't begin until we're at n is equal to 1. So we're going to kind of keep that in our back pocket. All right, but I still want to develop this general formula for my nth derivative at x, or at 2. My apologies. All right, let's look at the numerator. I get a 1, negative 1, positive 2, negative 6. All right, so it's alternating. All right, that we can definitely see. All right, this is definitely alternating. Got it. It's positive first, and then it's negative, positive again. All right, but this is at n is equal to 1. Remember, we're starting at n is equal to 0. So n is equal to 0 will lead us to a positive, but n is equal to 1 is also positive. So we need a positive here. So I'm just going to index this as 2n plus 1. Or actually n plus 1, sorry. There we go, n plus 1. That should work out. All right, if n is 1, then we get 1 plus 1 is 2. Then we get it to be positive. Perfect. N is equal to 2. 2 plus 1 gets us 3. Negative 1 to the power of 3 will get us that negative value. Awesome. Denominator kind of looks nice. The denominator looks like I'm just getting 2 to the power of n. So this is just 2 to the power of n. But now I need these coefficients. I get a 1, a 2, and then a 2 times 3. It kind of looks like I'm using factorials in the numerator. You might want to go through one more derivative iteration. So go through the 5th derivative and see if you can find this coefficient here. All right. Turns out that that coefficient more than likely is going to be n minus 1 factorial. Awesome. So what we have here so far is we kind of have this setup that we're looking at. That when we're trying to analyze this function here, we actually get to see this take place. And that's that our nth derivative evaluated at 2 is equal to negative 1 to the power of n plus 1 multiplied by n minus 1 factorial divided by 2 to the power of n. But there's an issue with this Taylor series, and the issue is that n is equal to 0 does not fit in here. It does not fit into the pattern that we have developed. So what are we going to do to alleviate this? All right. So what we're going to do to alleviate this is going to be this. We have f of x. We have the natural log of x. Oops, sorry. We have the natural log of x here. Now, I have this representation that I can use for my power series, or for my Taylor series. So my Taylor series is naturally going to begin at 1 in this particular case. So my Taylor series for my pattern begins at n is equal to 1. I'm leaving an open space here. My coefficients that I found are all these guys. So that's my numerator. So negative 1 to the power of n plus 1 divided by n minus 1 factorial, all divided by, we have 2n, but then according to Taylor series, right, we're also going to have an n factorial on that denominator. All right, so we're going to still be looking at this. So this is 2n, and again, we still have that n factorial in that denominator. All right, so far so good. And again, looking at my Taylor expansion, I'm coming all the way up here to the Taylor expansion definition. Here we go. The Taylor expansion definition says that we must have that n factorial in that denominator, and that's exactly why I input that n factorial in that denominator right in here. So this gives us all our coefficients, and that coefficient is being divided by n factorial, so there we are. And this is also x minus a, but in this particular case a is 2, so x minus 2 to the power of n. Now again, this only works beginning at n is equal to 1. Well, what about n is equal to 0? Well, since our pattern doesn't fit for n is equal to 0, we're just going to manually add this in. So I'm going to add in the natural log of 2 in manually, because again, it does not fit with the pattern beginning at 1 going all the way to infinity. So let's look at n minus 1 factorial divided by n factorial. N minus 1 factorial is just n minus 1, n minus 2, all the way till we get to 2 times 1. N factorial is n times n minus 1 times n minus 2, all the way till we get to 2 times 1. What happens? All these cancel, and we're just left with 1 over n. Which means this actually simplifies just a little bit more. We get the natural log of 2 plus the Taylor series beginning at 1, negative 1 to the power of n plus 1, n minus 1 factorial divided by n factorial simplifies to 1 over n. Therefore, my numerator still stays as x minus 2 to the power of n. My denominator now just becomes n times 2 to the power of n. And there you have it. This is the Taylor expansion for natural log of x. Isn't that amazing? I like that. Alright, it's looking really, really good so far. Now, at this point in time, this is how we want to discuss, and this is how we want to work with these Taylor and Maclaurin series. Alright, so I hope that you all enjoyed this lesson, and congrats, you made it through Calc 2. I will see you all in class.